Hello, AP Stat students. Mr. Hazelhorst here, coming to you live from room A08. Today we're going to start our first video in Chapter 5, Section 2A over probability models. All right. So again, just want to remind you this whole flip process, since it's been a while since we've kind of done the video thing. So I'm going to encourage you to take notes, stop the video as you need to. Notes are online. You can print those off and write right on top of the PowerPoint presentation that you're going to see me going through today. And again, as always, at the end of the video, there's going to be a form for you to fill out. So think about any questions or concepts you'd like explained in further detail, and leave comment of those in the form at the end of the video. All right, let's get rolling. We're going to jump right in with an example problem in today's video. All right, so let's imagine flipping a fair coin 3 times. Oh, excuse me. Let's get rid of that. So again, imagine flipping a fair coin 3 times. We want to give a probability model for this chance process. Okay. So chance process just means that we're doing some sort of activity or selection where things happen by chance. All right. So our process here is we're going to roll a coin or flip a coin 3 times. We know the outcome of that is determined by chance. So that's the model that we're setting up. All right. Now we're going to use this example problem to illustrate an important concept that we utilize oftentimes in probability models, and that's what's known as a tree diagram. And a tree diagram is just simply a diagram that's used to represent the sample space of a chance process, where each branch will represent a possible outcome. All right, so we'll go back and talk about that phrase sample space in just a moment, but let's go ahead and draw a tree diagram out for this setting. Now I could just ask you to list out all of the outcomes of flipping a coin 3 times, but the problem is I can't hear you since this is a video, and 2, we don't necessarily know when we've achieved all of the possible outcomes. All right, and so this is where a tree diagram becomes really, really helpful. So this is what our tree diagram would look like in this problem. Okay, so we're going to start at a point. That's the top of our tree, and then from there we're going to branch off. And so the first task that would have to happen here is we'd have to flip the coin 1 time. And so from that point, we would branch off to the outcomes that are possible in this setting. So when I flip a coin the first time, I'm going to get either a heads or a tails, right? So now we need to represent the second task. We need to flip the coin a second time. Well, the second outcome is going to come based off of the first outcome. So if I flipped a head the first time, well, then it's possible that I flipped a head or a tail the second time. If I flipped a tail the first time, it's possible again that I flipped a head or a tail. And so you can see that this tree diagram is growing as we add on more tasks in this chance process. Now, we wanted to flip this coin 3 times, so we need to do it 1 more time. And again, it's going to branch off of the last level that I've created. We'd have heads or tails, heads or tails, heads or tails, and heads or tails. Okay. Now, this is an example of a tree diagram. All right, you can see that each flip of the coin is represented on its own level. But again, as the flips of the coin kind of accumulate, we have to base off of what happened before. So when we look at this setting here, we can see there are 8 possible outcomes of flipping a coin 3 times, right? And we just determine that by going down each branch. So if I go down my first branch here all the way down on that left side, you can see one outcome would be heads, heads, heads. All right, if we just list out all the outcomes, we can also go heads, heads, tails. I'm just going to go across my branches from left to right. I could go heads, tails, heads. I could go heads, tails, tails. I could go tails, heads, heads. I could go tails, heads, tails. I could go tail, tail, head. And finally tail, tail, tail. And so those are all of our outcomes. Okay. Now, once we have a tree diagram and we have the sample space drawn out, it's very easy for us to answer probability questions. So if we wanted to then take this information and answer the question, what is the probability of getting 2 or more heads? Well, it's really easy now. Right? We know from a probability setting, well, I've got 8 different outcomes, so my probability will be out of 8. And I just want to see, okay, how many of these have 2 or more heads? Well, we've got our 3 heads. We've got heads, heads, tails, heads, tails, heads, and finally tails, heads, heads. So we have 4 different outcomes out of the 8 that produce 2 or more heads. And so our probability there, that would then be 1/2. Okay? Now, that's just a simple method to use to, again, find the sample space of simple probability settings. So with that done, let's talk about a few terms of probability, and we'll relate back to this problem. So we want to keep this image in our mind. All right, so the first term is that term sample space. So when we talk about a sample space, we're just simply listing out all possible outcomes that could occur in that chance process. So if we go back to our tree diagram on the previous problem, we had 8 different outcomes that were possible. Our sample space oftentimes is going to be abbreviated by the capital letter S. So as we work throughout chapters 5, 6, and 7 especially, if you see a capital S, that's referring to the sample space of that chance process, meaning it's the set of all possible outcomes. Okay? Now, the second term here is the idea of a probability model, and that's really what our tree diagram created. As it created the sample space, okay, which is one part of a probability model, and then from that sample space, we're able to figure out the probability of each outcome. If we go back, we had 8 separate outcomes that made up our sample space, and each of those would occur at an equal probability. So our probability model would say every item in our sample space occurs 1/8 of the time. All right, and then our final term is the idea of an event. All right, and this is just simply a subset of the sample problem. If we go back to the question that we asked, what is the probability that you flip a coin and get 2 or more heads? Well, that's an event. 2 or more heads is an event. It's a subset of our sample space that we created, right? The sample space had 8 total outcomes, but when we say 2 or more heads, well, that narrows it down to only 4 outcomes. Again, a subset. Now, off of that, we also want to understand some basic rules of probability. And these are pretty simple, but they're things that we need to keep in mind as we work throughout chapters 5, 6, and 7 especially. All right, so the first rule of probability is that the probability that any event occurs is some number between 0 and 1. So if we were to write that in probability notation, we say for event A, right, that the probability of A, that's what our P parenthesis A parenthesis is representing, is the probability of A, right? So the probability has to fall between 0 and 1. All right, if the probability is 0, that means that event is never going to happen. If the probability is 1, that means that that event is certain to happen, and it could fall anywhere in between. Now, the only time that sometimes this confuses students, that really it looks like a probability is over 1, is if we're representing probabilities in a percent, right? Then we would say that event A could be anywhere between 0% and 1%, or excuse me, 100%. But really, that's still falling between 0 and 1. If we convert that percent to a decimal, it still falls within this range. All right, our second rule of probability is that if we take all the possible outcomes from a sample space and we add all their probabilities together, all right, they have to equal 1. If something is truly a sample space, that means that it has, again, represented every possible outcome. And in any chance process, something has to happen from that sample space. So if we're talking about the probability that an event is within the sample space, well, it's got to be 1, right? Because the sample space contains all possible outcomes. Our third rule of probability is just simply the model that we use to represent a probability answer. So the probability that event A occurs can be found by, and again, we use that same notation, P of A, the number of outcomes corresponding to A. So A is our event, right, divided by the total number of outcomes in the sample space. So if you go back to the example problem that we began the video with about what's the probability of flipping a coin 3 times and obtaining 2 or more heads, right? Well, the number of outcomes corresponding to 2 or more heads, that was the numerator of our probability answer, and the denominator was representing how many outcomes were in the sample space, 4 out of 8, which we reduced down to 1/2. Okay? So 3 basic rules there, a few more to come here. So rule number 4 is the idea of the complement. Now notice how complement is spelled here. It's spelled with an E, not with an I. So we're not telling a probability that its hair looks nice, but it's the complement, okay? Meaning if I give you the probability that an event does occur, the complement is the probability that it does not occur. And the complement we will often see notated as A superscript C, and that's what you see here at the end of this line. Again, A superscript C. And the formula for finding a complement is very easy. If I know the probability that something does occur, the probability that it does not occur is just 1 minus that answer. So if I told you the probability that it was going to snow tomorrow is 20%, okay, well, the complement of that would be the probability that it's not going to snow tomorrow, which if there's a 20% chance of snow tomorrow, it means the complement of that event is 80%. All right, again, simple rule. Rule number 5 is just some important terms and phrases that we use within probability. So it's saying if two events have no outcomes in common, all right, and they can never occur simultaneously. All right, these are known as mutually exclusive or disjoint. Okay. Now, the easiest example I can give of this is think about drawing a card from a standard deck of playing cards. So we know in a standard deck of playing cards, we have hearts and diamonds and spades and clubs. Okay. And so let's say I had one event that is drawing a diamond and one event that is drawing a spade. Now, would it be possible for me to draw one card that meets the conditions of both of those events, right? There's no diamond spade card. So it can be a diamond or it can be a spade, but it cannot be both. So those events would be known as mutually exclusive or disjoint, right? They could never occur at the same time. And if events can never occur at the same time, then we have a really easy way to find their probability, right? So if we were saying the probability of A or B occurring, we simply add their probabilities together, okay? Because they're disjoint, they have nothing in common. Now, we'll piggyback off of this rule in the next video that you get to watch for this chapter as well. All right. Well, those are our 5 basic rules of probability. So now let's kind of put these into practice. So let's take a problem like this one. Okay, so let's say we were talking about M&Ms, all right, and the distribution of colors in M&M. So if I had a bag of M&Ms and the probability that I reach into that bag and draw out any one of these colors is listed out on the table that you see here. So the question that we have to answer first is, what is the probability of drawing a blue candy? Okay, now you might think, well, I have no idea, right? Well, we have enough information. If that is representing the sample space, that table is representing the sample space of color distribution amongst M&Ms. Well, we know if that is the sample space, that all of those probabilities have to add together to equal 1. And so with what we are given here, we have enough information to then figure out the probability of the blue candy, right? If I add up all of these probabilities that are provided within the table, right, the sum of these probabilities comes out to be 0.76. So again, if I want to find the probability of the candy is blue, right, well, it's got to be whatever is left over, because in order for this to be a sample space, it can only be a sample space if all these probabilities add up to 1. So that means the probability of drawing a blue candy would be 24%, or 0.24. Right? That's the only number that would be acceptable to plug in for the blue candy to make this a legitimate sample space. Right? Any other number in this would not be appropriate. Okay? So then our second question here, what is the probability of drawing a red, yellow, or orange candy? Okay? Now, is it possible to reach into a bag of M&Ms and pull out a yellow/red candy? Could we have a candy that's both yellow and red? Now, somebody might argue that's what orange is, but we're not going to go down that path, right? We're going to see these as 3 separate colors. So we need to recognize that this would be a situation where these events are mutually exclusive. I can draw red, I can draw yellow, I can draw an orange, but I can't draw all 3 of these or even 2 of these at the same time. So that means to find the probability, I'm just going to add those values together. So the probability of us pulling out a red M&M is 13%, a yellow M&M is 14%, and an orange M&M is 20%. So if we add those together, the probability of us drawing out red, yellow, or orange M&M would be 47%. All right. Well, that brings us to the end of our Chapter 5, Section 2A video. So I hope you are having a great day. Again, I want to recommend that you complete the video form below. Remember to rate your level of understanding and leave any comments or questions or concepts you would like covered in further detail in the notes section below. Again, have an awesome day. We'll see you soon.